are going to start our lecture on advanced reaction engineering. So, in this class we will discuss about multi-phase reactors. So, in our previous class we have discussed about the slurry reactor. So, today we will discuss about trickle bed reactors. So, in the details about the trickle bed reactors already we have discussed in our previous class also. So, this is similar like a slurry reactors. Here also gas and liquids that are the reactants that will be passed from a reactors. This is the reactors, here catalyst bed is there. So, inside of the bed catalyst are fixed. So, that is not movable component. So, that remain inside of the catalyst in the form of beds. So, when gas and liquid that is passed through this reactors inlet. So, that is co-currently downward through this pact of the catalyst, the gas and liquid will flow. Okay. So, here gas and liquid, that is the reactant that will flow, and inside of the catalyst bed there is some ports are available. Through that ports reactants molecules will pass, interact with the catalyst particles or solid particles, reactions will take place, and then product will come out from the with unreacted reactant component will come out from the reactors. So, this type of reactors industrially trickle bed reactors diameters are 3 meters let us say, and 3 to 6 meters, that is the length 3 to 6 meters and diameter 3 meters, usually that range, and reactor is filled with the catalyst particles that having the range 1 by 8 inch to 1 by 32 inch catalyst particles diameters within that range. So, in a range we can use, and the pores of the catalyst that is filled with the liquids. So, when liquid and gas both are passing through this bed of the catalyst. So, then the pores are available that would be filled with liquids, and here catalyst bed is fixed in this case. Okay. So, this type of reactors usually used for the earlier means very old type of reactor. This is actually used for the removal of organic matters in the waste waters. Suppose you have a wastewater stream. So, in that wastewater streams waste materials is there, organic waste materials may be. So, that if you want to digest in presence of aerobic bacterial action. So, in presence of that gas means air that we have to pass with wastewater, let us say liquid is the wastewater and gas is the air maybe. So, that both will pass through this catalyst beds, and then biological growth would be there, and then some organic materials, that microorganism that would be developed over the surface of the catalyst, and then that reactions means oxidation reactions means organic component that is present in the wastewater that would be decomposed in presence of airs. Okay. So, this type of things usually used for that means earlier or old methods, that is for wastewater treatments. Okay. So, nowadays means in chemical engineering point of view. So, that is the trickle bed reactor that is used for chemical industry, that is basically hydrodesulfurations of heavy oil stocks, hydrotreatings of lubricating oils, and there are some other also acetylenes, formaldehyde to butane diol. So, these are the chemicals. So, usually prepared by using one gas component, another liquid component or the reactant. So, these are the few examples I am showing. So, gas, liquid and solid phase reactions, in that case this particular trickle bed type of reactors we can use, and there is no the basic reactions and transport steps in the trickle bed reactors. The basic reactions and transport steps in the trickle bed reactors are the similar as we did or discussed for slurry reactors. So, here main difference is the correlations that we will use for the determination of the mass transport coefficients. So, that is the changes, means correlations is different, but basic reactions and steps are almost similar in case of the slurry reactors that we have discussed. Okay. So, here you can see means the red equation for the means here is the gas and liquid, that is the reactant, and here solid is the catalyst. So, here let us say this is the solid particles, gas is outside. So, it has a concentrations, that gas phase concentration CAG, and this is the liquid surface. Okay. This is the liquid surface, this is the solids and this is the gas. So, when gas in come in contact with the liquid, so then this is the called interface. So, interface gas concentrations or component A, and then it would be transferred to the liquid. This is the component at interface in the liquid side. the component A in the liquid sides, and then it would be transport to the bulk. So, this is the bulk concentration of the component in the liquid. So, the concentration of the component A at bulk, and this is the surface concentration CAS, that is the surface concentration. Surface means outside surface of the catalyst, the component A concentration CAS. Okay. So, individual points you can see. So, gas to solids or liquids whence reactant C is moving. So, individual points, so there is some resistance is there as we discussed for slurry reactors similarly, and the component concentrations also gradually decrease, or when gas phase component A concentration is high, and then it's once it is moving towards the surface of the catalyst, gas phase concentration it is decreased, but how that is. So, that if we notice here you can see the reactant concentration profile here I am showing. So, here in the x axis the resistance, and y axis that is the concentration of the component A, since A that is the gas and B is the liquid that is reactings in presence of catalyst, that is the solid catalyst, and product formation is there in this reaction. So, gas, liquid and solid. So, here component A, that is the gaseous component, initially it was very high when it is in the gas phase, then when it is coming to the interface concentration is going down. So, here this is the interface gas phase concentration, this is liquid phase concentration, but at the interface. Okay. And then liquid phase is coming, this is the liquid, this is the gas. Okay. This is the solid component. So, then from the interface to the bulk it is coming, this is the bulk concentration of the component A, and from the bulk to the catalyst surface it is moving, and then concentrations is here this CAS, and so once it is reached to the surface of the catalyst, then again it diffused through internal diffusions to the catalyst particles or catalyst pores, and then at the surface of the catalyst or inside of the catalyst where there are active sites are available, there reactant A, B and catalyst will be come in contact, and then at that particular space the reactions will be occurred, and then product formation should be there. Okay. So, this way the resistance is, this is gas phase resistance, this is liquid phase resistance, and this is internal resistance. That way we can also the concentration driving force is there as we did for the slurry reactors. So, now step 1 we want to know the gas phase bulk gas phase to the gas liquid interface, means at this particular point, that is the here this particular point. So, here the resistance or the rate of the transport of component A, how that is changes, rate of transport of A per mass of the catalyst R A prime minus R A prime, that we can write equals to kg into A I 1 by 1 minus E B into rho p, and this is the driving force C A G minus C A I. C A G is the gas phase concentration of the component A, and C A I is the interface concentration of the component A. So, this is the difference or driving force, concentration of interface, concentration at the bulk gas phase concentration, gas component concentration in the bulk, and this is the density of the particles, and E B is the void volumes, that is the volume of the solid to the total bed volumes, that is solid volume to the total volumes, and mass AI, that is the interfacial area per volume of the bed. So, interfacial area per volume of the bed, since we have taken a solid catalyst for the trickle bed reactors, there catalyst particles is there. So, it has a specified volumes and it also has a surface area. So, what would be the surface area of that catalyst particles present, that would be per unit volume of the interfacial area where the reactions will take place. So, interfacial area equals to per unit volume basis, okay, and this is kg equals to mass transfer coefficient, okay, kg is the mass transfer coefficient. So, now this is for rate of the transport per mass of the catalyst for step 1 bulk gas to the gas liquid interface, that equations we have to use. Okay. Similarly, for gas phase liquid interface concentration, similarly as Henry's law we have discussed in our slurry reactors. Similarly, also concentration of the A or solubility of A in liquids, that we can write in terms of Henry's constant and interface concentration. So, interface concentrations in the gas phase we can find out if we know the solubility Okay. So, now we are coming to the step 3, that is the interface, means once the reactant molecule say reach to the interface, gas liquid interface, from there to it will move to the bulk of the liquid. So, then for that the rate equations, means rate of transport per unit mass of the catalyst as we did. So, here per mass of the catalyst, rate of transport away per mass of the catalyst equals to, this equals to K L A I, similarly 1 by 1 minus E B rho P and C A I minus C A B. C A B is the bulk concentration, component A concentrations at bulk, C A I is the interface concentration, that is the driving force. Okay. Concentration of A in the bulk, concentration of A in the liquid phase interface, and rho P is the density and 1 minus E B is the volume of the solid to the volume of the bed, and E I is the interfacial area as we discussed, and K L is the liquid phase mass transfer coefficient. So, earlier one was the Kg gas phase mass transfer coefficient, since that was the gas to interface, and now interface to the bulk of the liquid, therefore, it is mass transfer coefficient is different, K L into A I, that is the liquid phase mass transfer coefficient that you have to consider when the transfer is from liquid to the interface to the bulk liquid. Next is the transport of bulk liquid to the catalyst external surface area. Similarly, as we did, so here's minus R A prime equals to K C A C into C A B minus C A S. Here the transfer or mass transfer that is going on, that is bulk liquid to the surface of the catalyst. So, therefore, here's we are considering liquid phase mass transfer, liquid solid mass transfer coefficient K C, external surface area per unit mass of the catalyst, and this is the concentration driving force that we are taken, that is the surface concentrations, and this is the bulk liquid concentrations. Okay. So, this is for the changes from bulk liquid to the catalyst external surface of the catalyst. Similarly, step 5, that is the diffusion and reactions inside of the pellets. So, after reaching the reactant to the surface of the external surface of the catalyst, then it moves to the pores of the catalyst. If we consider, let us say it is a first order reactions. So, then the rate equations we can write minus R A prime equals to eta K C A S into C B S, that is the rate equations, minus R A prime, that is the rate at actuals that we are getting, eta that is the effectiveness factor, that also we have discussed, specific reactions rate constant we have discussed, and CAS and CBS, that is the component concentration. That way we can write the rate equations for heterogeneous reactions, we can write this. So, now these are the 5 equations we have developed. So, now these 5 equations we are writing this way. Equations 1 is this, and equation 2, that is the interface concentrations of component A and with the by Henry's law. Here CAIG we can substitute here in terms of H, okay, H into CAI, that is the gas phase concentrations interface, and this is interface when after solubility of the component. So, from these correlations, and from equation 3 is this, equation 4 is this, that is the we have derived, and this is for 5th equation for internal diffusion and reactions equations. So, now these 5 equations where this equation will be put here. So, then we are getting 4 equations 1, 3, 4 and 5. So, from equations 1 we can rearrange and write this way. In the right hand side only concentration terms we are putting, here CIG we are substituting. So, here the equation 1 is this, and equation 2 is this, equation 3 is this, these equations, and these equations we can write this. Now, if we add all these equation left hand side and right hand side, then this part would be eliminated, only right hand side this part would be left, okay, and right hand side all these components would be left. Okay. So, now the rate equations we can write here minus R A primes, here also minus R A prime, here minus R A prime, here also minus R A prime is there. If you take out and then simplify the equations, it would be like this. These equations after summing up or adding from this equation 1 to 5. So, then minus R A prime equals to 1 by H and some constant into CAG. CAG is the gas phase concentration of the component A, or these equations we can write this. means overall whatever the constant terms is left in, that is we are putting as a kVg. Okay. So, overall mass transfer coefficient for the gas into the pellets, that is kVg. This rest, all these component terms we are expressing in terms of equation 7 as kVg. So, minus Ra primes we can write kVg into Cag. So, kVg is the overall mass transfer coefficient. So, this overall mass transfer coefficient, if we know, we can put it here at a particular concentration of the component A, the rate we can find out. So, kVg determination is very difficult. Okay. So, this part for system to system should be different. So, kVg is not a single component, this is there are so many parameters components are there. So, once we know individual components, if we put there in this equation 7, then only kVg we can get. Okay. So, how to find out this kVg value by considering this, that we will discuss in our later class, but now let us say the mole balance equations. For this is one kind of packed bed type of reactor. So, therefore, trickle bed reactor. So, therefore, the design equations we have to consider, that is packed bed type of reactor. So, dFA by dW equals to Ra primes. So, here's from this equation 6, this is also equation 6, you can say from equation 6 minus Ra prime equals to kVg into Cag into G. Okay. That we have derived. Okay. So, these red equations we can substitute here. So, then dFA by dW would becomes equation 8, that is equals to minus, here minus was there, here there was no minus. So, therefore, this minus we can put it here right hand side, therefore, it is coming this. Okay. So, this is the for component A, how component A is varying with this particular systems. So, molar flow rate of component A with the weight of the catalyst and corresponding gas phase concentrations kVg if we know. So, then we can find out Fa by W, that is the concentration of the component that it changes inside of this trickle bed reactor, that easily we can find out. Okay. So, this type of equations we have developed differential form of design equations or equation for this trickle bed reactor. Similarly, for component B also, means here our reactant was A and B, that is going to corresponding product in a trickle bed reactors. So, here the design equation for component A we have developed. Similarly, for component B also we can derive the equations. For component B minus Ra primes, earlier was Rab, and for component B we can write bulk concentration of the liquid, and this is the surface concentration. Since in a trickle bed reactors liquid is there, liquid inside of the reactors was there from the beginning when catalyst was there. Catalyst liquid B, that is the component B, occupied the pores of the catalyst bed. So, therefore, from that bulk liquid means present in the surface. So, this is the concentration. So, bulk to the surface concentration, and this is the means mass transfer coefficient for component B, and for then diffusions would be there, means once it is reached to the surface of the catalyst, then it move to the pores of the catalyst, as we consider or means determine for component A also. So, then similarly component B, rate of disappearance of component B, effectiveness factors, and this is the rate K CAS into CBS, similarly we can write. Okay. So, in case of the component B, equations 9 and equation 10 is coming. So, that is the step 6 and step 7, and 1 to 5 that was for component A. Okay. Red equations. So, now for component B 9 and 10 the equations we are getting. So, if we rearrange and similarly if we add both the equations 9 and 10. So, then we will get this, and these equations we can write minus Rb prime, that is equals to KVL into Cb. What is KVL? That is equals to this component is left, that we are writing as KVL2 for simplifications. Okay. So, for component B is the liquid and component A was the gas. Since component B is the liquid, then minus Rb prime, that is equals to KVL, L for liquid, and Cb is the concentration of the component B, and in case of the component A we have written minus Ra prime equals to Kvg. Component A was G, therefore Kvg and Cag. This is the rate equation for component A, and this is the rate equation for component B. Component B is the liquid and component A is the gas. This is the basic difference in between two rate equation for component A and B. So, if we want to know the Kvg value, then we have to use this constant equation 7, and if we want to know the KVL value, then we have to put all these component in this equation, then KVL we can get, and we can put in this equation 11, then rate equations easily we can find out. Okay. So, similarly for design equations, means this trickle bed reactors we can say, or design equations we are considering for a packed bed type of reactor. So, then dFB by for component B. Similarly, Bole valence equation or design equations we can write dFB by dW, that is equals to Rb prime, and a dFW equals to we can write equals to this Rb we are just substituting Rb prime equals to KVL into Cb, that we are substituting here. Okay, then this equation give this. Okay. So, from component A we have derived this and component B is this. So, equation 8 is for component A, that is the design equation, and for component B this is the equation 12 is the design equation. So, this is the differential form of design equations for trickle bed reactor for component A and B. So, these are 8 and equation 12. These two equations are the design equation for the trickle bed reactor for component. So, if we solve either this equation 2 or equation 6 and 11, so then we can get the mass transfer coefficient Kv and Kvl value, Kvg and Kvl value. Okay. So, these are the component we have to find out. Okay. So, then we can substitute this, or easily we can solve this equation at different concentrations, means Fb, Cb, W, like this Fa, Ca. These are the components at various catalyst if you are know. So, then we can solve these differential equations, then Kvg and Kvl value we can find out once we solve this ordinary differential equations. So, by solving ordinary differential equation solver by putting all these components. So, concentration of component A, component B, molar flow rates of component A and B, at thence we can find out the weight and corresponding mass transfer coefficient value KVL and KVG we can find out. Okay. So, today is up to this. Okay. So, here's all these already I have said, these are the two design equations we have, these equations and these equations we have, mole balance equations for component and A and B. Here you can see how we have solved this. This is we can solve, means this is differential equations by putting this value dFA, we can Fa equals to Fa naught into Xa, dFA equals to minus Fa naught Txa, we can do it and we can substitute it here, and Fa equals to Vg into Ca. So, dFA equals to Vg into dCa. So, this is normal molar flow rates component A and B, either this way or this way you can put, and after that we expressing this in differential form, and these equations we can, this is the DG equation for component A, we rearranging and integrating. So, then we can get this 0 to W amount of the catalyst, and here molar flow rate if we change. So, then dFA we can substitute it here this way, dFA equals to Vg into dCa, we can substitute it here, and then Ca into Ca out within that limits if we change. So, then after integrations we can get rearrangings, we can get W equals to Vg by Kvg ln 1 by 1 minus x. So, this is the means conversions and weight of the catalyst. So, if we want fixed conversion is fixed for a design for that particular reactions, then conversions value let us say x equals to 30% conversions we need for a particular reaction, we can put it here, and then Vg value volumetric gas flow rate if we know, and Kvg value if it is known, then we can put it, and then W value we can find out by using this. Okay. So, this way the catalyst amount necessary to achieve a particular conversion we can find out. Okay. Similarly, for component B also, so necessary weight of the catalyst is required to achieve a particular conversions of the component B also. So, this is the design equation or mole balance equation for component B, here minus KVL into Cv is there concentration of B. Similarly, if we integrate these equations as we did for that component A, so here we can get W equals to VL KVL ln 1 by 1 minus xb. So, VL is the volumetric flow rate of the liquids and KVL is the mass transfer coefficient, overall mass transfer coefficient for component liquid components. So, if we know these are the components and xb equals to let us say for 40% conversions we achieve want to get for this particular reactions, then we can put this value. So, and then amount of the catalyst that is required to achieve the conversions of xb, that easily we can find out. Okay. So, these are the things we have discussed. In our next class we will discuss about means the different mass transfer coefficient is there KVL and KVG, that is called overall mass transfer coefficient. These are the value KVG and KVL, how to find out mass transfer coefficient, that we will discuss. So, today what we have discussed about the trickle bed reactors and for a particular systems, and so how to derive the rate equations or steps by steps, means bulk gas phase to the liquid phase transport equations, rate of transport per mass of the catalyst, that is equation 1, and then say Henry's law, this step 2, that is the gas liquid interface concentrations or the solubility of the gaseous component in liquid, how to find out the concentration interface concentration, that Henry's law, and then interface to the bulk liquid, the transport from of component A, for that corresponding rate equation 3 we have derived, and then for bulk to the external surface of the catalyst the rate equation is this, and for diffusion and reactions the rate equation is this. These 5 rate equations we have obtained, and then we have correlated or rearranged all equations 1 to 5, and then we are getting the final rate equations. This is simplified equation minus R A prime equals to KVG into CAG. KVG is the overall transfer coefficient for the gas into pellets. Okay. Similarly, for liquid component also we have find out minus R B prime equals to KVL into CV, that equations we have developed, and then with the differential equations, this is the design equation or mole balance equation for component A in the reactors that we have adapted, and they are substituted this rate, and then final differential equation for component A and B we have developed, and these are the equations for component A, these are the component B. So, simultaneously we can solve, so we can get mass transfer coefficient or other unknown component from these equations if we know molar flow rate and corresponding weight of the catalyst, okay, and concentration of components. Okay. So, thank you. So, today is up to this. So, next day we will evaluate the transport coefficients of overall mass transfer coefficient and liquid phase overall mass transfer coefficient, how to find out those coefficients, and those are the coefficients that are very useful for the mass transfer calculations. Okay. Okay, thank you. So, today is up to this.